Second student completed an experiment to determine the enthalpy of neutralization. So you've got an acid and a base, or an acid and an alkali reacting together. The reaction between ethane dioic acid, where it's got two carboxylic acid groups, and potassium hydroxide. The student added 25 centimetres cubed of 0.8 mole decimetre cubed ethane dioic acid. So that means that we've got a volume and a concentration. We can work out number of moles. To 75 centimetres cubed of 0.6 mole decimetre cubed of potassium hydroxide. Again, we've got a volume and a concentration. We can work out number of moles. We've been given a temperature increase, so maybe we're using Q equals minus MC delta T. Given equation for the reaction between ethane dioic acid solution and potassium hydroxide. So I've got this here. You maybe remember ethanoic acid and sodium hydroxide makes sodium ethanoate, CH3COO H and NaOH makes CH3COO Na and water. So we've got the same kind of thing here. So but we've got two carboxylic acid groups, and so we'll need two potassium hydroxides to make two waters. So the hydroxide part reacts with the acid part, so the OH part reacts with the H of the carboxylic acid and makes water, and the potassium reacts where the H has been, so you get COOK, and at this end you'll get COOK. So same kind of reaction, as I say, between ethanoic acid and sodium hydroxide to make water and sodium ethanoate, but we've got potassium instead of sodium, and we've got two carboxylic acid groups at either end. Okay, let's have a look at the next bit then. So for the calculation, well, first of all, before I sort of go into this part of the calculation, I know why I've been given a volume and a concentration of ethane dioic acid and a volume and a concentration of potassium hydroxide. That's to work out moles, so let's do that. Concentration moles divided by volume, so for the ethane dioic acid, concentration 0.8 equals moles divided by 0.025 moles, multiply the two together to get 0.02. Same for the potassium hydroxide, concentration 0.6 equals moles divided by the volume 0.075, moles is 0.6 times 0.075, 0.045. Just remember, you're not using centimetre cubed, you're converting centimetre cubed into decimetre cubed, smaller unit into a larger unit like a decimetre cubed, then you divide by 1,000, and that's why I've used 0.025. I've converted the 25 centimetres cubed by dividing by 1,000 into decimetre cubed, and similarly for the 75 centimetre cubed, I've divided by 1,000 to get 0.075. So that's where those two numbers have come from. Okay, the next bit then, I know that if I've been given a temperature change, and more importantly, I've been given a specific heat capacity, the only equation that I know with specific heat capacity is Q equals M minus MC delta T, or delta H equals minus MC delta T. What's the mass? Well, the mass is the volume of the liquid. I've used 25 centimetre cubed and 75 centimetre cubed. So I've used 100 centimetre cubed of solution, and it says assume the density of the reaction mixture is 1 gram. So 1 centimetre cubed is 1 gram. I've got 100 centimetre cubed. I've got 100 grams of liquid. Remember, it's the liquid. This equation refers to the amount of liquid that you have that you're heating up. Specific heat capacity 4.2, temperature change 3.2, minus 1344, and it's in joules. So that's my heat change. Potassium hydroxide is in excess. Ethane dioic acid is the limiting reactant. What I mean is that there's plenty of potassium hydroxide. The reaction stops and that amount of heat is given out when the ethane dioic acid is used up. Because look, there's only 0.02 moles of ethane dioic acid. There's more potassium hydroxide. So ethane dioic acid is the limiting reactant. Even if I use 1 mole of this with 2 moles of potassium hydroxide, as seen in the first bit of the equation, this doubled is 0.4, this is 0.45, so I've got an excess of potassium hydroxide. It's this using up. When this gets used up, then the reaction stops and that amount of heat is given out. So we've got to work it out now. I've got minus 13344 joules of energy been released exothermic minus when I've used 0.002 moles of ethane dioic acid. The question is, how much calculate the enthalpy change per mole of water. Well, first of all, I'm going to do it per mole of ethane dioic acid. How much would 1 mole of ethane dioic acid give out? So what I've got to do is I've got to work out what I multiply by. So I do 1 divided by 0.02, which means I've got to multiply by 50. Those slightly stronger at maths will just multiply 1 divided by 0.02 by this value here. But I'm scaling up by 50 times. Minus 1344 times 50 is minus 67200 joules. That's how much energy is given out when 1 mole of ethane dioic acid is used. Now the question says how much per mole of water formed. So let's have a look back in the equation. 1 mole of ethane dioic acid makes 2 moles of water formed. So I've worked out how much energy is given out when I use 1 mole of ethane dioic acid. It's asking me how much per 1 mole of water. So I'm making 2 moles of water. 1 mole of ethane dioic acid makes 2 moles of water. How much energy would be given out if I only made 1 mole of water? I've clearly got to half this. I've got to divide this by 2. So if I divide minus 67200 joules by 2, I end up with 33,600 joules. It's asked me to work it out. It's not actually asked me to work it out in kilojoules, but if I were to work it out in kilojoules, then I'd divide by 1,000. You usually have the value in kilojoules per mole, minus 33.6, but it hasn't specified for me to put it in kilojoules per mole, so minus 33,600 joules will get you the mark. In a similar experiment, the enthalpy of neutralization for the reaction between sulfuric acid and potassium hydroxide was found to be minus 57.0 kilojoules per mole. So, in other words, sulfuric acid and potassium hydroxide is more exothermic, minus 57 kilojoules per mole instead of minus 33.6 kilojoules per mole. Why is that? So, sulfuric acid is a strong acid. It's fully dissociated. So it's fully broken up into H pluses. There's no sulfuric acid, it actually breaks up fully into H pluses. So being a strong acid, therefore you're going to get a more exothermic reaction because you've not got to use any of the energy to dissociate the acid. So less energy is needed to dissociate the sulfuric acid. So I'm not going to need any energy in actual fact to dissociate the sulfuric acid. It's already fully dissociated. So whereas with the ethane dioic acid, then here, because it's not fully dissociated, you're going to need to use some of the energy that's released to actually dissociate that ethane dioic acid. So your answer to get the marks, for the 2 marks for this, is all you need to write is sulfuric acid is a strong acid, so less energy needed to dissociate the sulfuric acid. The rest of it sort of explains really what I've just been talking about.